So our second speaker is Bill Tiffany from SigmaSense LLC, raised the verification need. Bill has an extensive background in digital logic verification, design and verification, including DSP applications, networking interfaces, microcontrollers, solid-state drive controllers, and with SigmaSense's latest touchscreen controller. In addition to understanding system requirements, continuous learning and sharing within a team is key to success. Couldn't agree more. Over to you, Bill. Thank you.
Thank you. Yeah, SigmaSense is a small company. They're a young company. They're based here in Austin. They have a deep background in this sensing technology, and a very short marketing description is fast, continuous, low voltage data capture with intelligent digital signal processing, which moves analog challenges to the digital domain, where software-defined sensing delivers orders of magnitude improvements. So the technology is not specific to touchscreens, but this latest SoC we've developed is a touchscreen controller. It's an evolution of previous generation designs. The touchscreen itself has a lot of pins. Some are rows, some are columns. And our analog, which is configurable by software, has a bunch of pins, each of which can be configured as needed. So the customer can wire up the SoC any way they want to the touchscreen controller, and then we'll configure the analog channels as needed to interact with rows and columns. On each pin, we both drive and sense signals onto each of the pins into the touchscreen. Touchscreen itself is a passive device, and basically what we're sensing is a change in impedance. So there's, as you approach or touch the screen, you're going to change the impedance seen down the rows and columns and change the coupling between the rows and columns. So our technology is focused on that. We have a custom DSP. On the transmit side, we synthesize various frequencies, and where software can control the amplitude, phase, and frequency of each waveform. And those are combined as needed on a channel-by-channel basis, filtered and driven out through the analog onto either rows or columns. On the receive side, we have kind of several stages. On a per channel basis, we have custom filtering, which is configured by software. We have discrete Fourier transform to move into the frequency domain. And then we have post-processing on that frequency domain data. And then firmware, it takes it from there and does further processing and then interacts with the host over an interface. So it's a simple controller. All the digital will easily fit into one FPGA. So from a verification perspective, we do have a test chip has the silicon and some of the digital. So an FPGA can be connected to our analog test chip and actually wired up to actual touch screens. So system engineers and firmware can actually debug their the operation with real touch screens. From a DV perspective, we had two test bench styles. One was the SoC as a whole. The analog part of the SoC, we used a real number model that was tuned against the SPICE simulation. So it's kind of calibrated to be as close as possible to the SPICE. And that gave us a good, accurate system level simulation environment. So in that one, we write the test in C code, compile them, and execute on the CPU. My focus was primarily on the DSP. So we have a test bench environment for the DSP where we have AXI and APB VIP for configuring and accessing the registers and memory. And then we have stimulus models to generate stimulus data that can emulate what might come off of a touch screen. It's quite a bit of hierarchy and you know, both parallel and serial processing of data in the transmit and receive domains. So there's quite a bit of, we had a hierarchy of test benches, if you will, in the DSP. And for an SoC development, we're a fairly small company, and we partner with TSolve to do the silicon development. Background on our DSP methodology. So we use MATLAB modeling, and in there we keep refining the system architecture to achieve the desired performance at a minimum gate count. And once, and that's to the point of optimizing the data path width at each stage of the digital pipeline. Once the system engineers are happy with that, then it's quite straightforward to extract the RTL design requirements from these detailed MATLAB models. And then from a verification perspective, we used two approaches. The first one used by design engineers, we'd create a simple system Verilog test bench, and then we can run MATLAB simulations and save off file with arrays of data in a system Verilog format, stimulus and expected results, and then run those in this system Verilog test bench. And then for the DV team, we used MATLAB's DPIGEN, which will basically convert the MATLAB into C code, C functions, and bring that over to our Linux environment. And we use that, though, the C models for our predictors for the DUT and also for the stimulus generation. So in a given simulation, well, I think I'll jump to the next slide, which is more of a picture. So the MATLAB specific components are here on top, the predictor, and over here, the stimulus. So in a given test sequence, we would say for a given, say we're going to emulate a given mode of operation of the touchscreen controller. So we might configure some settings as fixed and then constrain randomization for everything else. So for example, setting frequencies, phase, amplitudes, which channels we're using, which channels are rows, which are columns. That all gets defined via randomization constraints. Then we basically create a sequence item that carries that information. It gets passed down. The register values will get passed into the DUT via our APB VIP. Any memory initialization will go through the AXI VIP. The first stop will be the stimulus generation. So our register values will be used to customize the stimulus for that particular simulation. Also things we need to know, like touchscreen processing is done at a certain frame rate, and a certain frame will carry a certain number of data samples. So we have a sampling rate that's on the analog to digital interfaces. And so for a given number of frames, we'll need to compute the appropriate number of samples in the stimulus. So the stimulus is basically put into an array that gets added to the sequence item, it's passed to the driver, that he extracts the stimulus data, and the sequence item is passed on to the predictor, who will predict all the results, both intermediate and final output results, and add those predictions to the sequence item, which then goes to the scoreboard. And then in kind of real-time domain, the driver will, on a cycle-by-cycle basis, apply a stimulus. The monitor will be picking up DUT results, internal and external, and passing those on to a scoreboard cycle by cycle. So in the scoreboard, we're going to be checking on a cycle by cycle basis and indexing into the arrays of data provided by the predictor. And similarly, in the test, we may read registers or memory via APB, AXI, and those results are connected to the scoreboard as well. So it's, I think, a very basic UVM test bench and methodology. So MATLAB is a product of MATHWORKS, who also has a product named Simulink. We don't use Simulink, but I wanted to cover it here because from an ASIC flow, they provide very good support as well. It's GUI-based, it is cycle-based, which may be more intuitive for RTL and DV engineers. As far as ASIC flow support, you can export C models, you can export a system Verilog test bench. They also have a utility UVM build, so you can generate a UVM test bench associated with a Simulink model. We didn't use it just because we have a long history of MATLAB and expertise in that area. MATLAB has similar support other than UVM build. So as I said, we have a lot of long background in MATLAB for architectural and implementation modeling. The MATLAB DPIGEN utility exports DPI-C models, and those integrate very seamlessly into a system Verilog test bench. You can also export a test bench from that as well if you don't build your own. As I mentioned, MATLAB is sample-based, so we may be, for a given frame, we may be generating thousands of data samples over many channels. So those are, when we invoke the MATLAB function, we're creating all of those at once when we call the function. So, and then on the interface to the DUT, like the driver and the monitor, those are accessed, and sample at a time, and then given to the DUT on a clock cycle. So when you first invoke the functions, that can consume a fair amount of memory and take some time. So it may appear the simulation's just sitting there because the C code is chunking away trying to compute all the results. And so in our case, we can operate in a continuous mode where we're just continuously transmitting data and processing received data. And that's a challenge for simulation in the sense that we can really only simulate a rather small number of frames. If you tried to run a simulation for 1,000 frames, you might spend a long, long time with the C model just trying to produce that much data and consuming a lot of memory. So our simulations typically run in on the order of an hour or less, and we didn't really have any problem there. Okay. Some of the key issues, DPIGEN does enforce some syntax restrictions. So there was some code modification required. That was pretty minor, and if you add this CodeGen comment in MATLAB, it just highlights anything you may need to address. The biggest thing for us was MATLAB stores arrays in memory in a vector format, as does system Verilog. But there's a constraint on variable size, multi-dimension arrays. So DPIGEN requires those to be flattened before they appear as input and output arguments. So any results we want to come out of the C function, that had to be flattened inside of the function. And so a lot of the MATLAB code had to be rewritten to flatten arrays going out of a function, then reshape them coming into the next function. And then again, in the UVM test bench has to deal with that flattened array. So you have to understand the different dimensions in the MATLAB and how it was flattened in order to index properly. A few other things where we're kind of not so major is just MATLAB indexing is 1 to n versus 0 to n minus 1. MATLAB array flattening by default is column major order, whereas System Verilog has row major order. So it can cause confusion for the DB or RTL designer trying to figure out where the data is in those flattened arrays. Also, you have to deal with MATLAB data types versus System Verilog. So most of our MATLAB functions had double precision data types, and those get translated to real data type in System Verilog. And then at some point, those have to be converted to logic data types. And then I have a few slides here which touch on just the process of using DPIGEN. So MATLAB runs in a Windows operating system. So DPIGEN produces a zip file with .c, .h, and .sv files. So you bring that over to Linux, unpack it, and run GCC. And they provide an example GCC script. So that was pretty straightforward. Include the .sp file in your file list. You need a -dpi in your simulation command line and a pointer to the shared object file. And then, for example, in the predictor, we declare the C handle, and then they provide a function to initialize that. And then an example of a function that had the variable size output array, it gets split into two. So you feed all the inputs into the first function and you get out the size of the array. And then the second function call will basically initialize or load the values into that array. Summary, important to get agreement between like the RTL designer, MATLAB designer on the module partitioning interfaces, important signals you want to monitor, because you need alignment between MATLAB and the RTL, and then just come up with the methodology of dealing with indexing if you have these flattened arrays to deal with. Other than that, the use of the C models was just worked fine, no issues there. So it's a very seamless process of using those C models in my experience. Thank you very much.
Thank you, Bill. Any questions in the room? Yeah. Yeah. Let me get the mics. Remember, there's people on the mics. So. Okay. Testing.
Appreciate it. Thank you for your presentation. In your block diagram, I saw that you use MATLAB model as a benchmark, right? Because we do
predictor. Yeah.
Right. But I'm wondering if you are implementing there the model of the functions that you run in the DSPs or the model of the DSP itself. Because in the RTL,
it is the system architect writes the MATLAB, and then we take that MATLAB and convert it to C, and that's our predictor. And so the RTL has to match what the system architect creates.
And what you have in your RTL, do you have the actual implementation of the DSP as well?
The RTL?
In the RTL block.
The RTL designer takes a description of what's in the MATLAB. Typically, the system engineer will create a block diagram of, say, a digital filter, and the RTL designer will code from that.
Okay.
And so, yeah, we're comparing the system architect's definition of the function to the RTL implementation.
I got it.
Yeah.
All right. Thank you so much.
Yeah.
How does that analog phase frequency amplitude is getting converted in terms of the APB transaction?
What happens from the receive inputs to the output?
Yeah. How do you extract that in APB? APB in terms of APB. Do you have
there's a lot of stages of processing, but data comes in from the touchscreen, we filter it, and then run it through discrete Fourier transform, so that's in a frequency domain. And then we actually have quite a few different post-processing steps that firmware can select. Like basically what you're doing in the touchscreen is looking for a change, right? Because if nobody's there, nothing's happening. But somebody touches it, then things change. So we call it baseline subtract. So you have a baseline, you're subtracting the input from that, and then boom, somebody touches it and you see a change. So, and that goes into memories and they get DMA'd out over AXI.
Yeah, I think my main interest is how that analog is translated in terms of post-processing. That's all.
Okay, yeah, you can catch me outside too. I can probably better understand your question.
Okay, thanks. I'm just looking for Ben. Okay, hi Ben. Okay, so coming up to our final talk now. And our final speaker is Ben Del Sol from UVM Gen. So we'll just get him mic'd up. Yeah. And I'll make the intro. Thanks, Bill.